In this section of the class, we're going to introduce the idea that things that we used to model with the concept of a wave in classical physics can also be modeled with the idea of a particle. And in fact, both models are correct descriptions for the same thing. This is somewhat unfamiliar to us, but because we're used to solving problems in terms of models which rigidly apply, what we're going to be seeing here is that models will do perfectly well at describing certain aspects of phenomenon, but also have to be recognized as incomplete descriptions of what nature really is. Electromagnetic radiation is one example of something that was described very commonly with a wave. And in fact, this is one of the defining intellectual achievements of the 19th century. Right up there with Newton's laws of the 1700s and the 1600s came Maxwell's laws of the 19th century. So in addition to providing a unified picture of electric and magnetic forces caused by fields, E and B fields, Maxwell's laws allowed us to have a first description of light in terms of traveling electric and magnetic field waves, which had a speed miraculously coming out to be exactly c. The velocity of the propagating electromagnetic wave was 1 over the square root of mu times epsilon naught, and that turned out to be numerically equal to c. As a wave, electromagnetic radiation should obey the laws of superposition and therefore exhibit signs of constructive or destructive interference. And in fact, that was seen. Light does that. And that is, light was thought of as a wave, not as a particle, and the kinds of demonstrations that it had wave-like properties were things like Thomas Young's experiment on light with a double slit, or the experiments on X-rays done by Lowy and Bragg scattering off of crystals that showed constructive interference. In the 20th century, however, it became possible to describe electromagnetic radiation by virtue of a particle. The particle was called the photon, and its arrival was sort of signaled by three major insights. The first came from a physicist by the name of Max Planck, who in 1900 was devising a scheme of electromagnetic radiation to describe so-called blackbody radiation. And in order to come up with a correct mathematical formula to describe blackbody radiation, he had to devise a scheme in which radiation came in packets, which he called quanta. And the quanta of energy obeyed a relation of a constant h times frequency, where f is the frequency of radiation. And h is some new constant of nature, not yet known. In devising this packet scheme, he could then correctly describe the electromagnetic radiation spectrum from a so-called blackbody, a dark object that's emitting thermal radiation. It's interesting to note that Planck himself rejected the idea of really thinking of this as a particle, as was later espoused by Einstein, and he thought of his quantization scheme, this packet, as purely a formal assumption or a heuristic. He didn't actually think much about it in terms of being a new insight to how to describe electromagnetic radiation. He was just trying to quantize this energy spectrum so as to get a mathematical agreement with a formula, or with data. Planck received his Nobel Prize for contributions to quantum theory because the first idea of a quantized or discrete valued quantity came from him. The next step in the photon hypothesis, however, comes from Albert Einstein, who in 1905 had what's often been called a miraculous year, publishing 5 papers, each of historic significance. The first of these was an analysis of Heinrich Hertz's photoelectric effect and why it happened. Einstein suggested that electromagnetic radiation actually comes in not only discrete packets of energy, but he really referred to them as particles, and they were thus the photon. Einstein found that if he used Planck's idea of an energy packet of h times a frequency, he could explain all the results of a photoelectric effect experiment, and then he only had to have this new idea of a model where electromagnetic radiation came in particles. For this work, he received the 1921 Nobel Prize. The kind of slam dunk for the photon hypothesis came from another physicist by the name of Arthur Holly Compton, who in 1922 devised an experiment to show that X-rays act like billiard balls or particles. He showed it in his experiment that particles could go, or X-rays could undergo elastic scattering with electrons, just like billiard balls do. And in this process, he used some of the same tools of momentum and energy conservation that we learn in first-year physics. As a result, he was able to predict a shift in the wavelength of the scattered X-rays, and he received a Nobel Prize very quickly in 1927 for this work because it was so defining and showing that the photon did in fact act like a particle or a billiard ball in collisions. So what is a photon exactly? It's a packet of energy, and if we imagine a stream of electromagnetic radiation, we can view it either as a wave of electric and magnetic fields or a stream of particles. Each particle will have an energy E, which is equal to h times f. F is the frequency of the traveling wave, as we're using classical physics words like a wave. And we're talking about a particle, so we're starting to use quantized or particle type language for this thing as well. Planck's constant h is a new constant of nature. It's just like the electron charge or other fundamental constants out there, the gravitational constant. It happens to have a value of about 6.626 times 10 to the minus 34 meters squared kilograms per second. However, I encourage you never to learn this number. I don't remember it, and most physicists practicing in science do not remember it either. Instead, one remembers typically the product of h times c, which has a very convenient value of 1240 eV times nanometers. That's the number that most physicists remember, and I encourage you to remember it as well.